Okay, let's go over the problems from yesterday's in-class problem set. First one, using only the field axioms, prove that for any real number a, -1 times -a equals a. So to do this, we're going to first show that we first notice that -1 times -a plus -a equals -1 times -a plus 1 times -a. Then using the distributive law, -1 plus 1 times -a, which equals 0 times a, which equals 0. So -1 times -a, when we add -a to it, we get 0. And we're using the fact that multiplication by 0 gives us 0. This is actually an assumption. It's not one of the field axioms, so really we ought to be proving it independently. But we'll just assume that for this proof. Okay, so now what? So we've shown that -1 times -a plus -a equals 0. So if we take -1 times -a and add 0 to it, well, 0 is the same as -a plus a. So we now get that -1 times -a equals -1 times -a plus -a plus a. And using the associative law, that's equal to -1 times -a plus -a all plus positive a, which equals 0 plus positive a equals a. And that completes the proof. And as I said before, we are assuming that a times 0 equals 0, which isn't one of the field axioms, but we'll let that one go. So that takes care of that. Second problem, give an example of a bounded infinite set which has a max and a sup, or a sup but no max. Well, those are pretty easy. The closed interval 0, 1 has a max of 1 and a sup. Open interval 0, 1 has a sup, namely 1, but no max, no maximum element. Here's where things get interesting. True or false? If S is a bounded set, and X is less than sup S, then there exists an element of S which is strictly between X and sup S. That feels like it ought to be true, but it's not. Suppose S is the set closed interval 0, 1, union 5. So it's certainly a bounded set, and sup S equals 5. 4 is certainly less than sup S, but there's nothing in the set between 4 and 5. Notice that in the statement of the theorem, the S we're looking for is supposed to be strictly between X and sup S. It's supposed to be greater than the element X, or the number X, but it's supposed to be less than sup S. And the only thing in S that's bigger than 4 is, in fact, sup S. So what is true is that F is a bounded set which does not contain its sup, and X is less than sup S, then there's an element strictly between the two. So you need that extra condition that the set S does not contain its sup. So here's the proof. Since X is less than sup S, and sup S is the smallest upper bound for S, X must not be an upper bound for S. So there must be an element S in S which is bigger than X. Now, since sup S is an upper bound for S, we have S is less than or equal to sup S. Upper bound means you're greater than or equal to everything in the set. But the equality doesn't hold because sup S is not an element of the set S, and little s is an element of the set S. So little s must be strictly less than sup S, and that completes the proof. And finally, if x is any real number, then there exists a natural number which is greater than x. So this just feels so true, and it is, of course, but you can't prove it just using the field axioms and the order axioms. You have to have the completeness axiom. You have to have the least upper bound property of the real numbers. So suppose the theorem is false. Well, then there'd be at least one real number x which was greater than or equal to all natural numbers. but that would make x an upper bound for the natural numbers, which would imply that the natural numbers has a least upper bound by the completeness axiom. Now, that sup of n cannot itself be a natural number, because then you could add 1 and would get a larger natural number. So by the previous theorem, there has to be a natural number satisfying n, which is greater than sup of n minus 1/2, but also strictly less than sup of n. So here we're using the fact that sup of n is not a natural number to find a natural number which is within 1/2 of sup of n. And so we're using that previous theorem that shows that if you have a set and the sup is not contained in it, and if you take anything smaller than the sup, you can find something in the set between that smaller number, sup of n minus 1/2, and the sup of n. Okay, so what? Oh, now we add 1 to that first inequality, which gives us sup of n plus 1/2 is less than n plus 1. But that makes n plus 1 a natural number greater than sup of n, and that's your contradiction. So this was pretty fast, but feel free to watch the video several times, and please ask about things that still seem hazy to you. Have a great day.